All right, let's go ahead and get started, everyone. Today we're going to continue talking about currents in the ocean, which we had started on Monday. And it's possible, but perhaps a bit ambitious, to say we might get to waves a little bit, but we'll probably start those in earnest on Friday. Today will probably mostly be about currents. This slide's also a good excuse for me to talk about in the day after an election, even though it wasn't really one in Los Angeles. Ben Franklin, one of our founding fathers, was actually a great scientist in many ways. Everybody knows about his contributions to the study of electricity and flying a kite during a lightning storm and all that stuff. But actually, he was one of the first people to chart out the path of the Gulf Stream. He realized by talking to sailors, particularly merchant sailors, but also naval sailors, that the merchants had figured out that taking the shortest route from Europe to North America actually took much longer than following a line of latitude, more or less, from Europe to North America, and inferred from that there was a current actually running off the east coast of North America that was pushing boats towards the east. And so he actually sketched out a pretty good map of the path of the Gulf Stream back in the middle 1700s. This was even before the American Revolution. So the study of the Gulf Stream is actually pretty old and ties into a lot of American history. All right, so on Monday we talked about this idea of gyres, these loop currents, these circular currents that are spun up by the prevailing winds in the trades and the westerlies. So going from a little bit away from the equator up to about 45 degrees or so north and south of the equator in each hemisphere, in each ocean. So that there's a North Atlantic gyre, a North Pacific gyre, and 3 Southern Hemisphere gyres in the South Pacific, the South Atlantic, and the Indian Ocean. And in each case, the equatorward part is being driven towards the west by an easterly prevailing wind across the ocean basin. And there is a current away from the equator that's being driven by the prevailing westerlies that goes from west to east across the ocean basin. And then up against the coastlines, against the margins of the continents, at the edges of the oceans, there are boundary currents, east and west boundary currents, that are essentially returning water from where it piles up against the continent on the downwind side to an area where water is being pulled away from the continent on the upwind side of a different wind band. Okay? So we end up with these more or less circular currents, 5 in each hemisphere, 5 total over the globe, and you can see that that's actually not all that's going on here. There are some other currents in here. We talked about the Antarctic circumpolar current, which goes in the same direction as some of the gyre currents and is related to them, but actually goes all the way around the planet rather than being deflected by hitting a continent. And there are some other little gyres in the North and South Pacific, for instance. And we also talked about this idea that the fact that the currents are going clockwise in the northern hemisphere and counterclockwise in the southern hemisphere means that they function as high pressure systems, that water is being deflected towards the middle or inside of these loops of current, so that you actually build up topography. And the topography is steepest in the areas where the current is fastest and most intense. So that, for instance, off the east coast of North America, where the Gulf Stream runs up like this, okay, where the Gulf Stream runs, the fastest current, the western boundary current, is also an area where the sea surface is getting higher very quickly as you move offshore. So here we're going in cross-section from right here over to right here, someplace in the middle of the North Atlantic Ocean. And you can see that the ocean actually jumps up by something like 50 or 60 centimeters in this particular image, right where the Gulf Stream is. And in fact, you can infer from the steepness of this curve how fast the Gulf Stream is going. And then very gradually, as you move farther into the ocean basin, that hill begins to come back towards the mean, indicating that the eastern boundary current and the currents in most of the Atlantic, North Atlantic, are much more gentle. They can't support as steep a hill. And this is true of all the gyres, and of course it's dynamic. When the gyre currents are going fast, you're going to build a big hill. When the gyre currents are going slow, you're not going to build as big a hill. But you can see here the Gulf Stream building these sort of red-peaked hills in the middle of the North Atlantic Ocean, really big hills in the Pacific, both south and north, and also particularly in the southern part of the Indian Ocean. Okay? In all cases, these are currents that are a balance between the circulation of the gyre currents and the tendency of Coriolis to push water towards the middle of those gyres. Okay. So are there any questions now about gyre currents, about the idea of having some extra water, a high pressure system in the water because of the deflection of those gyre currents? Yes? What we're looking at here is actually a departure. This does have a, so the question is, does this not have anything to do with the geoid? And actually it does. What we're looking at here is actually a departure from the geoid. So the geoid would be, where is the ocean sitting if it's not, if there are no currents, if it's not circulating. So it can just find sort of the lowest area to rest in. And because these currents are spinning in the oceans, they're actually causing the surface of the ocean to depart from that sort of minimum energy surface and make hills and valleys. So what we're looking at here is a defect relative to the geoid caused by the dynamics of the ocean. And so again, this is telling you that something is dynamic, right? Because the ocean's not in its minimum energy state. We have hills, okay? If there wasn't something making those hills, it's water. Water doesn't stand being in a hill. It'll just spread out. So this is telling us right away that the ocean is dynamic. Something is driving it. Something is making it move to sustain those hills. Any other questions? All right. Now there's one set of currents that was visible on that sort of global cartoon map I showed you that isn't the Antarctic circumpolar current, which is driven by westerlies. It's not the gyres, which are also driven by westerlies and trade winds, but it is driven indirectly. And those are the equatorial countercurrents, which occur right at the equator, typically between an equatorial current associated with the northern gyre and an equatorial current associated with the southern gyre. And these are currents that occur right at the equator, so right away you should be saying to yourself, okay, that's a little weird. The equator corresponds to the boundary between the two trade wind belts. That's a region where air is predominantly rising. It's not really moving sideways along the surface, not really in a consistent direction anyway, not a strong prevailing wind. So there's not really a wind to drive a current there. Okay. And there's no Coriolis effect at the equator. You're kind of going from the rightward Coriolis north of the equator to the southward Coriolis, so the leftward Coriolis south of the equator. So it's not like something is being deflected there. So there's not much wind, there's not much in the way of a Coriolis to bend some other current into that region. So what turns out to be happening there is actually the absence of those things. What's happening in the equatorial currents, they're pulling water across the ocean basins towards the west and making piles over here. And so there's extra water over here. Right along this line, there's not actually very much wind, because you're in the doldrums, you're between the two trade wind belts. There's not very much Coriolis, or almost no Coriolis, so a current, once it starts going, can actually pretty much go in a straight line without being deflected. It's the one place on the planet where that can happen. And so therefore, in that area, this hill of water can just relax back to the other side of the basin. Okay, it's the one place on the planet where there's not really much wind to speak of, not much Coriolis, so any piles of water can just relax across to the other side of the ocean basin. So what happens right at the equator is that you get a current going from west to east, the opposite direction from the equatorial currents driven by the trade winds. And these currents are stronger at some times than others, and they're certainly stronger in some ocean basins than in others. But they're interesting because of they're kind of exceptions to this idea of gyre currents, but actually they make sense in the same context. And you can see them here. Here's an here's the Atlantic equatorial countercurrent. Here's the Pacific equatorial countercurrent. Here's the Indian equatorial countercurrent. Let's go back to this one again. So we have equatorial currents that are pushing water over here. as the surface water is going across this basin, what's happening to its temperature? Or at least what might you expect to be happening to its temperature? This water comes down from somewhere closer to the poles, gets close to the equator, and starts getting dragged towards the west. Yeah, it's going to warm up. So you might expect to see lots of really warm water over here, maybe warmer than it is over here, because the water that gets here at the equator was actually not that long ago pretty close to, or farther away from the equator in a colder region. There's actually more going on that we'll get to in a minute that makes it colder. But that's one reason you can imagine. So if you have an equatorial countercurrent, what might you expect the water associated with that current to be like? It should be warm, right? Because it's taking warm water back across the ocean basin along the equator. Okay, so the equatorial currents are actually transporting water towards the west across the ocean basin, piling up warm water on the western parts of ocean basins, making the western boundary currents work. Okay, but the equatorial countercurrent is actually a current that's capable of bringing warm water back the other way towards the eastern part of an ocean basin. All right. Any more questions about surface currents in the ocean? Okay. So we're going to focus in on one special thing that happens when these currents circulate around in the surface ocean. This is a picture of the North Atlantic again, and hopefully you can all now recognize the western boundary current, the Gulf Stream, this very intense current that runs off the east coast of North America. But if you go to the other side, okay, water's cooling down because it's far away from the equator, and you can actually follow, looks like there's some really cold water here, looks like there's some pretty cold water here right up against the coastline. And in fact, the water right here is colder. It's like a greenish or bluish color, which indicates colder temperatures on this map, than the water even north of it, right? There's a little sliver of really cold water right along the course, in this case, coast of Portugal. And there's also pretty cold water along the northwest coast of Africa. So we're seeing something special happening in those places, okay? Cold water is coming down because of the eastern boundary current, and it's getting pulled back across the basin. And actually, in these places, particularly along the west coasts of the continents and the eastern sides of ocean basins, you're actually bringing up cold water from some depth. Okay, so not only are you bringing cold water down from the polar regions, or at least the poleward parts of the gyres, but you're actually pulling up the colder water, the denser water, from depths and bringing it up to the surface. And this happens in a few places in the ocean with some regularity or some intensity, and it's going to turn out to be important for when we start talking about biology, because as we've talked about, this water that's been deep in the ocean, particularly if it's been down for a while, it's kind of composted. It's had decaying organic material in it while it's been at depth below the depth in the ocean where sunlight can penetrate. It's built up a supply of nutrients. When that water comes back up into the sunlight, it's really fertile grounds for biological activity. Okay, so places where upwelling happens tend to be places that are biologically very rich. Okay, so upwelling is important because it's a way to bring nutrients into surface waters where photosynthesizing organisms can take advantage of them. And it's particularly caused by areas where you have divergence of surface waters. If you're pulling surface waters away, you have to replace that water with something. We don't make holes in the ocean, at least not very big ones. And so what tends to happen is deep water will come up to replace it. And when you bring that water up into the sunshine, the little critters go crazy. They really like that. And so this is mostly a dynamic process. In particular, tends to be caused by effects of wind driving surface currents and being affected by Coriolis effects. You can also have upwelling and especially downwelling caused by density effects. When water gets up near the North Pole or the South Pole, it becomes really dense and it can sink down to the bottom. And of course, there's got to be a conservation. If water is sinking one place, it's got to be coming up somewhere else. So let's look at a couple of ways you can drive upwelling in the ocean with winds and Coriolis effects. One of the most important causes of upwelling occurs at the equator. So here we're imagining, again, a rectangular ocean. And we have the equator going across, okay, the doldrums. And then north and south of the equator, we have trade winds, right? And we're in the equatorial parts of the gyres. So we would expect to have currents that are going from east to west. Now we're near the equator, so Coriolis effects are pretty weak, but they're still there as long as you're not actually on the equator, okay? And which direction would you expect the Coriolis effect to deflect this equatorial current north of the equator? Towards the right. Which way would you expect Coriolis to deflect this current south of the equator? To the left. So we have these currents that are actually being pulled away from the equator. Weakly, but it's happening. So what's happening? We're diverging the surface flows. We're pulling the surface of the ocean away from the equator. And so what's going to happen is, if this is happening intensely enough, it's going to be able to actually pull deeper water up to the surface to replace it. So right along the equator, because Coriolis goes in different ways north and south of the equator, you actually can pull up deeper nutrient-rich water. And you can see this upwelling. What might be one way you would detect that upwelling was happening along the equator? Okay, you could certainly look for a strong biological productivity. That's definitely one thing to do. And we'll see some pictures of that, actually, as we get beyond the second midterm. Is there anything we've talked about already that you might use to detect upwelling? I showed you a picture where I said upwelling was happening near Portugal and the coast of Africa. What was the evidence that the upwelling was happening there? Yeah, in particular, what about the temperature? It was cold. So here we're near the equator, right? The area that's most intensely heated by the sun. So if we have upwelling and we're bringing up deep water, we should see a cold spot that kind of sticks out like a sore thumb in the warmest part of the planet. And that's actually what you see. This is actually a computer model, but it's driven by data. And this is the Pacific. So here's South America, Central America. We're right up here in Southern California. And of course, the reds here are really warm, of order 25 degrees Celsius or something like that. But right along the equator, past the Galapagos Islands, here you can see there's this wisp of yellow colored water, in this case yellow indicating temperatures of order 20 degrees C or less. Okay, so we're seeing water brought up to the surface that is several degrees Celsius below the water just north and south of it, and it's not because of solar heating. Okay, this whole area is being heated pretty intensely by the sun. This is evidence instead that we're bringing up water from some depth and mixing it at the surface. So we're diverging surface flows and bringing up deep water to replace it, bringing up nutrients, and you would expect that wisp, at least a week or so later after biology has a chance to respond, to be an area where biological productivity increases. Okay, that's not the only place where it can happen. And in fact, the first picture I showed you was something different. Portugal's not on the equator. You can also have upwelling along the coast where you cause a divergence of surface currents. And this actually takes advantage of the coast itself as being a boundary to the ocean. So let's imagine we're in the northern hemisphere, like in California, along the west coast. And in this case, let's imagine we have a wind that's blowing from north to south. What kind of surface current is that wind going to generate? Is it going to generate a current going this way? This way? This way? Who votes for this? You want to vote for this one? Okay. Yes. Because Coriolis and the Ekman spiral that I talked about, the surface wind is going to generate a surface current in the northern hemisphere that's deflected towards the right by something like 90 degrees, at least the net current. So in this case, a surface wind going from north to south will tend to create a surface current that's actually moving offshore. Okay, so we're pulling the surface waters away from this coast. Well, there's no water over here to replace it. You're at the coast. So the only way to replace that surface water is to bring up some deeper water. Okay, so this is another place where you're pulling the surface current, pulling the surface water away. In order to replace it, you have to bring up deeper water. If the pull is strong enough, you can even pull up denser water that's colder and has been at depth and has accumulated nutrients and cause upwelling. Okay, and here's just a little block diagram to sort of give you a 3D view of the same process. Sorry for the north and south. For some reason, when I look at this, I think north and south should be reversed, but this is just the way the figure was made. So if we have a wind blowing from north to south along the California coastline, we generate a surface current that's going offshore, and to replace that surface water, water gets pulled up from depth right along the coastline. So we should expect, wherever that kind of thing happens, that we should see areas of cold water being brought up along west coasts in particular. Okay. So you can see it off the coast of Morocco and Portugal. You can also see it here in the southern part of Africa, off the coasts of Angola and Namibia. And these tend to be common along west coasts of continents. They're not as consistent as the equatorial upwellings. It depends on which direction the wind is blowing. It depends on how intensely the wind is blowing. And it depends on the shape of the coastline. So it can vary with the weather, in fact. And in California, upwellings tend not to be consistent events. They tend to occur episodically. We'll have a period of upwelling associated with some weather event, and biology will respond to all the new nutrients, and then it'll kind of shut down for a while. Okay. Why should we expect that this upwelling is more likely to happen along west coasts than east coasts? It does happen, by the way. You can have upwelling along an east coast by the same mechanism. The wind would have to be blowing a slightly different direction. It would have to be blowing from south to north in the case of the northern hemisphere, but that happens, certainly. But it's more difficult to upwell water along the east coast of a continent than along the west coast of a continent. Why? I'm sorry? There's a water hill, but actually that doesn't extend all the way to the coastline. By the time you get to the east coast of the United States, you're actually at the bottom of the hill because you're on the outside of the Gulf Stream. But there's another property of the water there that's important. So everywhere along the gyre, both the western boundary current and the eastern boundary current are being affected by Coriolis in such a way they tend to get pulled towards the middle. So that's, in principle, you can get upwelling along east coast for the same reason that you can get them along west coast. But there's something different about the water in the western boundary current than the water in the eastern boundary current. It's not quite it. So we have a gyre current, an eastern boundary current. Where is it coming from? Here. Where's the surface current coming from? Somewhere up here, right? So what's the temperature of that water? It's probably pretty cold. And in fact, you can see it here, right? We're getting these kind of yellowish colors instead of the really intense red colors. If we were to go over to the other side, to the Gulf Stream side, where is the Gulf Stream water coming from? It's coming from like the Caribbean. So what's its temperature like? Warm. Okay, which water is going to be less dense? Warm water. And in order to upwell, right, you have to replace the surface water with deep water. So which area is going to have the stronger pycnocline, strongest density gradient between the surface water and deep water? The western boundary current, right? Because there's really warm, not very dense water at the surface. It's going to take a lot of energy to pull all that water out of the way and replace it with much denser cold water at the surface. Okay, so because there's a strong thermocline, not very dense water sitting at the surface, it takes lots of energy to drag all that surface water away and replace it with deep water. Over here, the surface water is already pretty cold because it's coming down from somewhere near 45 or 50 degrees north of the equator. It doesn't take as much energy to drag that water offshore and replace it with cold deep water because the density difference isn't that great. Okay, so the strength of the stratification of seawater, the difference between the densities of the deep water and the surface water actually controls how easy it is to mix vertically or how easy it is to replace surface water with deep water. In areas where that density gradient is large, where the surface water is warm, it's very difficult to replace it with deep water. You have to do lots of work to replace replace less dense water with more dense water at the surface. Eastern boundary currents, not so hard because the surface water is colder. Okay, let's take that argument to its logical conclusion. If this is an area where the water is sort of moderately cold already, so it's pretty easy to replace it with deeper water, what's going to be the part of the ocean that's easiest to do that kind of vertical mixing in? Yeah, near the poles, right? Where the surface water is really cold. In fact, it's so cold in many places that it's almost the same density as deep water, and that's where deep water is actually formed. So we should also expect, by the same argument, to see evidence of upwelling near the poles. And I put my slides out of order, but in fact that's true. So this is a picture of Antarctica. So this is the South Pole, looking down on the South Pole. Southern South America, Southern Africa, Australia. And in this case, as one of you mentioned, we're detecting evidence of upwelling not by looking at temperature, but in fact by looking at the abundance of chlorophyll, which is, in this case, giving us some idea of the intensity of photosynthesis. Chlorophyll is the pigment that phytoplankton use to do photosynthesis with. So you can imagine a part of the ocean that has lots of protein designed to do photosynthesis is probably doing lots of photosynthesis, and thus by inference probably has lots of nutrients in it. You can see right along the coast of Antarctica, there are all those red and yellow colors indicating high biological productivity. Surface water is already cold there. It's not very hard to bury that surface water and bring up deep water to replace it. So there's usually lots of nutrients in the polar waters, relatively speaking. Okay. So if we put all this together, we can kind of make a global map of where upwelling occurs. And it really occurs at the equator all through the oceans because of this equatorial divergence. But also along the west coast, there's usually pretty good upwelling activity. To some extent along east coast, in fact, anywhere along the coastline, you're likely to find some decent upwelling. Okay, and then also near the poles. Okay, so there are a few parts of the ocean that tend to have upwelling, that tend to have lots of nutrients, and thus tend to have lots of biological activity. The equators, west coast, near the poles. The middles of the gyres, well, you can see, right? Here's the North Atlantic gyre, here's the North Pacific gyre, Indian Ocean gyre, South Pacific, South Atlantic. Those are like the deserts of the ocean. Once you get inside the gyre, you're well away from the continents, no coastal upwelling. By definition, if you're in the gyre, you're not at the equator, you don't have equatorial upwelling. Those are high pressure systems. Surface water is actually piling up there. It's converging. It's not being pulled away. So those are parts of the oceans where it's actually very difficult to bring deep nutrient-rich waters up to the surface. And therefore, those are regions of the ocean where biology is relatively sparse unless there's some special adaptation that allows photosynthetic organisms to make do without very many nutrients. All right. Any questions about that? All right. So we've talked about surface currents. And the one thing I definitely want you to remember about surface currents is that we're mostly talking about currents driven by wind, either directly in the case of the transverse currents or indirectly in the case of the western and eastern boundary currents. When we talk about flow in the deep ocean, of course they couple to the shallow water. Everything we've talked about with upwelling has to do with an interaction between surface currents and deeper waters in the ocean. But in general, when we talk about deep water circulation in the ocean, we're talking about flows that are driven by differences in density rather than directly being driven by wind blowing across the surface of the ocean. So once we get below a few hundred meters in the ocean, really what we're talking about is water that sank there when it got really cold, sometimes a little bit salty, near the poles. And it's simply filling up the ocean basin and displacing all the other water there, because these are the waters that are the most dense, and so they can sink and displace anything else. It turns out, in the modern ocean, the formation of new deep water, the back ends of these arrows, don't occur everywhere near the poles. In fact, they only occur in a few places along the planet. Okay? So this is a little figure I stole from MIT, online course. And the little red dots here actually indicate areas that are important for the formation of deeper waters in the ocean. And there is basically one region off the coast of Antarctica, the Weddell Sea, which is responsible for formation of some of the densest waters in the ocean. There's one or two areas in the North Atlantic Ocean that are also responsible for forming the deepest waters in the Atlantic Ocean, at least the North Atlantic Ocean. It turns out that the Mediterranean Sea doesn't form really deep water, which hopefully makes some sense to you. The Mediterranean is not a pole, okay? It's not actually very cold. It's actually usually nice and warm. If you've ever been to Israel or Rome or someplace along the Mediterranean, the weather is actually a lot like California, maybe even hotter. But it turns out that for a special reason, you make a layer of water that's below the surface. That's important there. So we can kind of count on one hand and actually have a finger left over, a couple fingers left over, all the places where deep water in the ocean forms. All the places where water gets so dense, it sinks down below the surface and fills up the bottom of the ocean basin. And the basic story, particularly for Antarctica, but you can sort of generalize from there, is that the formation of the densest waters in the ocean require a kind of combination of factors. It has to be close to the poles, so you get really cold water, and salt water gets denser the colder it gets. So that's where you're going to form the water that's able to sink to the bottom. But it also helps if you can make the water a little bit salty. If you can make the water a little bit salty and really, really cold, it's going to get super extra dense. So it turns out that in places, for instance, off the coast of Antarctica, where winds can actually generate these sort of open areas on the ocean surface, and sea ice starts to form because, of course, the climate might be much colder than freezing, even the freezing temperature of ocean water. When you start to form ice at the surface of the ocean, the ice that you form is much fresher than the water that it forms from. Salt does not like to go into ice. So if you make ice at the surface of the ocean, you have to exclude salt from it. That salt gets left behind. So you have very cold water. It's so cold it's freezing. Okay? And you're adding some extra salt to the liquid part of that water because you're removing fresh water to make ice. Okay, so it's really, really cold water, and you're giving an extra boost in its density by shoving some leftover salt into it. So it's in those places where you make the densest waters in the ocean, and they can actually spill over and essentially fill up the deepest parts of all the ocean basins. Okay. So below a couple kilometers or so in the world's oceans, you can actually trace waters back to a couple places on the planet's surface, 2 or 3. The North Atlantic is an area where we form a body of water that we call the North Atlantic Deep Water, or the NADW. Okay? And the North Pole, particularly since the Arctic Ocean is kind of restricted in its access to the Atlantic Ocean, doesn't quite make as much really cold water as Antarctica does. But it turns out that there's a tendency for water to get fairly salty there, partly because of the gyres, which are areas where surface water builds up, and it actually turns out to be regions near 30 degrees, because that runs right through the middle of the gyre, where the air tends to be very drying because it's sinking between the two wind bands. And so that mixture of fairly cold water, maybe not super cold, with fairly salty water can make water dense enough to sink. And then in the Antarctic, or off the coast of Antarctica, that's where this process happens to its most extreme level. You get really, really cold water forming sea ice, expelling salt. So you have very cold, slightly salty water, not as salty as the North Atlantic deep water, that can actually sink and make the densest water in the oceans today. Okay, so how do we why do we even bother making these names, right? It's deep water, it's all cold. Salinity's not actually that different, although we'll be able to see the difference. So how do we sort of fingerprint, where is water coming from? How do we tell the difference between North Atlantic deep water and some other kind of water? Well, there are various things you can use. We can measure chemical properties and temperature and salinity in seawater. And it turns out that these different processes in locations where deep water is made impart different signatures into the seawater when it sinks that are preserved at some level of fidelity even over hundreds of years. So let's take an example. I mentioned that the Mediterranean, which clearly isn't the coldest part of the oceans, nonetheless forms a part of the ocean that isn't right at the surface. It forms waters that actually sink below the surface. And you can kind of see why if you just look at a map of salinity. So this is the amount of salt dissolved in surface waters in the ocean, particularly in the North Atlantic, going from, in this case, purplish colors, which are like 3% salt, up to these deep red colors, which are like 4% salt. Most water in the ocean is very close to 3.5% salty. By the time you get up to 4% salty, that's kind of extreme and weird. And you can see that where do you find really salty water in this picture? Where's the saltiest water? Yeah, you find it in the eastern Mediterranean, okay, off the coast of Egypt and Israel and Lebanon. Where else do you see it? Not in the Atlantic, but you certainly see it in, for instance, the Red Sea, which is just peeking up here. You also see it in the Persian Gulf. But let's focus in on the Mediterranean. Okay, Mediterranean's quite warm, but it's really, really salty. And it turns out that the reason the Mediterranean gets so salty is because it sits pretty close to 30 degrees north, this area between the trade winds and the westerlies where the Hadley cell and the Ferrel cell come together and air sinks. It sinks, it compresses, it warms up, its ability to hold on to water vapor increases, and so it becomes very drying. It wants to suck water out of anything it comes into contact with. Okay, and so in the case of the Mediterranean, it sucks the water right out of the surface of the Mediterranean, and of course you have the Sahara Desert to one side, and really southern Italy and Spain aren't the wettest places on the planet either. And so in net, it turns out that the Mediterranean loses water. It loses more water than it gains from the rivers that flow into it. Okay, so in fact, the Mediterranean draws water out of the Atlantic Ocean. Okay, so there is water at the surface coming in through the Straits of Gibraltar between Spain and Africa, and it comes into the Mediterranean Sea and evaporates and becomes saltier and saltier and saltier. Eventually it gets so salty, it actually becomes denser, even though it's quite warm, than the water that came in from the Atlantic, and it sinks underneath it. Okay? And it sinks underneath, and it fills up the basin, and then it flows right back out again. So at the Straits of Gibraltar, there are actually two flows. At the surface, water from the Atlantic is coming in, okay, to keep the Mediterranean Sea from evaporating away. And at depth in the Straits of Gibraltar, the water is actually flowing out again after it's become really, really salty. It's still pretty warm, because it was last at the surface near Israel, okay? But now it's much saltier, so salty it's pretty dense. And it spreads out into the Atlantic Ocean because it's so salty. So that if you look at a depth of about 1,000 meters in the North Atlantic Ocean, and you contour by salinity again, although the units here are a little different, you can actually see that there's kind of this big tongue or wedge of salty, turns out to be pretty warm water, down as deep as 1,000 meters in the North Atlantic Ocean, and you can sort of trace back from the less salty parts of it to the most salty parts of it right here. We can sort of fingerprint this water by its salinity and also by its temperature. It must have come from here. Okay? So we can actually trace back using salinity in this case and find the origin of a body of water in the deep ocean. Yes? Yeah. So the reason this water gets so salty is because when it comes in from the Atlantic, it comes into a basin that's dry most of the time. And so the seawater is evaporating away. It's getting saltier and saltier and saltier until it sinks because it's so salty it's dense. And then it flows back out again. All right. Has anybody seen Das Boot? I know that movie's getting kind of old now. In fact, there might not be anybody in this room who was actually born when that movie came out. A couple of you have seen it. So the climax of the movie, the movie's really scary in lots of places. It's a great movie, by the way. The movie's really scary, and the part where they get assigned, so it's about a crew of a German submarine, so they're kind of anti-heroes in some sense. And they're assigned to go from the Atlantic into the Mediterranean Sea, which is like suicidal during World War II because the British are patrolling the Straits of Gibraltar with everything they've got because they want to keep the Germans out. Okay, so these guys have to figure out, how are we going to get past these guys, the British guards, and get into the Mediterranean Sea? And their clever but unfortunately not very, well, unfortunately for them, not successful strategy is simply to sail their boat until they get somewhere off the Straits of Gibraltar and just submerge and turn the engines off so they can make no noise and hope that they drift into the Mediterranean Sea. Okay? And of course, that strategy is only going to work if they don't go too deep. If they go too deep, they're going to end up entrained in this really salty water, and they're going to go right back out into the Atlantic Ocean. It turns out it doesn't work anyway. British planes spot them, they actually get bombed, and they end up sinking all the way to the bottom. Oh well. All right. So let's play somewhat similar game on a broader scale. We've kind of figured out, okay, how can you trace water that's coming from the Mediterranean into the Atlantic? Let's look at the Atlantic as a whole. Let's take a cross-section going all the way from Iceland on the north end to Antarctica on the south end, looking at depth going from the surface down to more than 5 kilometers. And of course, the ocean's not that deep everywhere, so where there's white here, that's actually the seafloor. Okay, and we can, in this picture, in this cross-section, we can actually see this water coming out of the Mediterranean by its saltiness. There's this blob of water at about 30 degrees north that's extra salty, and it's pretty deep. And you can infer from the fact that it's salty and deep, but not all the way at the bottom, that it must be fairly warm. Okay, it can't be denser than this less salty water underneath it, so it must be much warmer than that water is. And so we can actually fingerprint Mediterranean intermediate water at a depth of 1,000 meters or so in the North Atlantic. And we can see a couple of other bodies of water. You can see this very not saline tongue of water, also at about 1,000 meters depth, coming up from the southern hemisphere, from Antarctica. You can see medium salty water going underneath the Mediterranean intermediate water and gradually spreading out. That is the North Atlantic deep water that's formed off the coast of Greenland. Okay, it's cold. It's not quite as salty as the Mediterranean intermediate water, but it's definitely pretty salty. And then right off the coast of Antarctica, we see this kind of not super salty, not as salty as the North Atlantic deep water, tongue coming in underneath the North Atlantic deep water. It's less salty than the North Atlantic deep water, but it's denser than the North Atlantic deep water because it's flowing underneath it. So that must be even colder than water that was off the coast of Greenland. Okay, so this is the coldest water of all. Okay. So we have this kind of interfingering of water coming from the North Atlantic, kind of getting sandwiched between a couple tongues of water coming up from the Antarctic. Okay, in this case, we can fingerprint them using salinity, but we could also look at a map of temperature. We could look at a map of nutrients like phosphate, for instance, and we could actually come up with a very similar picture. Figure out where that water was last near the surface. And also, and I've mentioned this, right, if you look at something like Freon, CFC, you might even be able to figure out how old that water is. How long has it been since the water was at the surface? If this part of the North Atlantic deep water is less than 50 years old, it probably has CFCs dissolved in it. If it's older than 50 years old, it shouldn't have any CFCs in it because CFCs weren't really invented and used broadly until about 50 years ago. Now it gets a bit more complicated when we look at other oceans. So if we do play the same game in the Pacific, going from, let's see, Antarctica up through the Pacific, past Hawaii, which some of you might be able to see if you're in the front row, it's kind of smudged out, all the way up to Alaska, we can see that Antarctic bottom water again. The color scale here is a little bit different, okay, but it's somewhat saline water. And it's kind of making a big tongue that essentially fills up the entire Pacific Ocean. The North Pacific doesn't really generate deep water the way the North Atlantic does or the way the southern oceans do, because the Aleutians in the Bering Sea are actually very shallow. And they kind of prevent really cold water from forming in great volume there. So there isn't really deep water being formed in the North Pacific, at least not today. Okay, so the whole Pacific kind of gets filled up by this mixture of waters coming off of Antarctica. You can see that there's some water, very fresh water, that must presumably be quite cold in the North Pacific, but it doesn't get cold enough and salty enough from ice formation to actually fall down and displace the Antarctic water. All right. If we put together this idea of cold waters forming in a few places near the poles and tracing how those waters move by using properties like their salinities and their temperatures and their nutrient abundances, we can actually kind of generate a cartoon, and this really is intended as a cartoon, not gospel, of a conveyor belt, a way of transporting heat and nutrients in deep water around the planet, with a few places near the poles where water sinks, okay, a few discrete places, and then once it sinks, it spreads out and fills up the deep parts of the ocean basins, spreads out into the North Pacific, and then is eventually brought up by processes like upwelling. And that cartoon, this idea of formation of really dense water near the poles in a few places, particularly where you have sea ice forming, and circulation of surface currents driven by winds, and upwelling, putting it all together, we can talk of an idea of thermohaline circulation, density circulation in the ocean, where dynamics overcomes the tendency of the ocean to stratify by temperature and by density. All right? So are there any questions about that? All right, so I want to show you the first couple slides about waves to have you think about them, and also because I think they're really cool. Okay, this is a movie I shamelessly stole from Oregon State University. This is actually a wave tank called the Hurricane Wave Tank. And the movie takes just a couple minutes. So we've generated a wave. Hopefully everybody can see it moving. And then it's about to hit a little concrete wall that they built. Except the concrete wall doesn't really last very long. Just plows right through it. And in a minute, you'll actually see, if you look, you can see cinder blocks and things actually splashing around in the water. Okay, this thing is a wave. It was human scale, and it blew right through a concrete wall, or it was actually like a cinder block wall. Okay, and you can clearly see that there's something moving here, right? There's a wave moving down this tank from one side to the other. So the question I want you to think about for Friday is, what's moving here? What's being transported in a wave? And how does that contrast to what's being transported in a current? So I'll see you on Friday, and we'll start talking about waves.